Hello and welcome to the third of the lectures in this week 7 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this week of lectures, we have been discussing similarity-based reasoning, and we have seen that a fuzzy inference system approximates a given system function by covering it through overlapping rule patches. This is the most important takeaway when you want to visualize how a fuzzy inference system captures the working of a system. We have, of course, through the previous two lectures, seen the operations involved in similarity-based reasoning. In this lecture, we will discuss Mamdani Fuzzy System. Before going towards seeing how it is implemented in the Matlab fuzzy logic toolbox and using it to build Mamdani fuzzy systems, we need two preliminary things: to look at matching function in a slight generalization, and also to understand how Singleton Fuzzification works with such class of matching functions. Then we will go on to build one particular function through a Mamdani fuzzy inference system, that is approximating that function by building a Mamdani fuzzy inference system using the fuzzy logic toolbox in Matlab. Well, a quick recap of the similarity based reasoning, the different steps involved. We are given a set of single input, single output rules. The first step is, given an input A dash, we want to match it with each of the antecedents. Now, for this, you are given an A dash, you will match it against each of the antecedents A1, A2, so on till AN. What we need is a matching function for this. So essentially, the matching function takes two fuzzy sets defined over X and throws out a similarity value which is typically in the 0-1 interval. So you could look at it as a normalized matching function. So M is from f of x cross f of x to 0, 1. Given an A dash, the similarity value of A dash to AI is what is captured by this matching function in the value Si. We have seen a couple of matching functions in the previous lecture. We will have occasion to see these presently too. So that's the first step. So given an A dash, you have matched it against all the antecedents and we have got similarity values. The next step is to modify, using this similarity value of the corresponding rule, modify the consequent of the corresponding rule. So S1 is the similarity value between A dash and A1. We use this S1 to modify B1 to get a B1 dash. Similarly, A dash and AI, you get a similarity value of Si using a matching function. Use this Si to modify Bi to get a Bi dash. These are some of the matching functions that we have seen. In fact, we have seen that these are essentially fuzzy logic connectives. So what you see here, this is a T-norm and this we know is the Gaussian implication. In the third step, we aggregate all of these Ba dashes, B1 dash, B2 dash, so on and so forth till Bn dash. These are the modified consequence. We aggregate all of them. Once again, we have seen that it is sufficient to consider associative fuzzy logic connectives. Typically, T-norms or uninorms are used for this. Finally, there is also another step. You could defuzzify this. That means the obtained output set is a fuzzy set B dash on Y. Now, we would typically need a value in the domain of Y. So, we apply a defuzzifier and get a value Y in the domain Y. Some of the defuzzifiers are the centroid, mean of maxima and so on. We will see these in little more detail visually when we implement using Matlab. There is also another step that is there. That is, typically if you are given only a value and not a fuzzy set, then we do the reverse of defuzzification, which is called the fuzzification. We have seen how to obtain a singleton fuzzified value of a given input. Also, we have seen how to obtain triangular fuzzification or Gaussian fuzzification. Well, let's look at matching function a little deeper. Matching function essentially is a function from f of x cross f of x to 0, 1. Now look at these two examples. These are some of the often used matching functions. If you look at them closely, what you have here is actually a function outside and a function inside. So essentially it is more like a composition. In fact, the Zadeh's maximum matching function is essentially the maximum composition of two vectors. So when you look at it like this, it is in some sense a generalization of composition of two vectors. So you need two operations here, and that is how we can look at them. So in the case of Zadeh's matching function, the O times operator is actually min, and the operation that is outside is max. In the case of Smith-Magre matching function, the operation inside is an implication and the operation outside is the minimum T1. Well, typically these are a major class of matching function that are considered. Now, let's look at how Singleton Fuzzification goes with this class of matching functions. Let's consider these two examples and a Singleton Fuzzifier. So given an input x0, what we do is we create an A dash to be given as input to this fuzzy inference system, which is a fuzzy set on x. So A dash at x0 with respect to x0 is defined like this. It takes the value 1 at x is equal to x0 and 0 elsewhere. So in some sense, it is the characteristic function of the classical singleton set x0. Now, consider the Zadeh's matching function, and let's assume that we are giving it an input which is a singleton fuzzified input. Let's look at what happens to the similarity between A and such an A dash. So mz of A dash of x0, if you were to write it in terms of formula, we substitute for A dash, we substitute A dash of A dash x0. Now, this can be split into two parts. The first part is, consider all those x in x which are not equal to x0 and separate out when x is equal to x0. Now look at this region. When x is not equal to x0, what happens to A dash x0 of x? It is essentially 0. When x is not equal to x0, then it is essentially 0. So what we are looking at is, this part A dash of x0 of x is actually 0. Now what happens to A dash x0 at x0? By this definition, it is 1. Now, minimum of anything comma 0 is 0, because we know 0 is the annihilator for the T norm, especially in the case of minimum. So no matter what x you take here, whatever the value of A of x may be, this whole thing turns out to be 0. Now minimum is a T norm, 1 is its neutral element. So from here what we get is 0 max A of x0, which is essentially A of x0. Well, let's look at what happens in the case of Smith-Magre modification matching function. Once again, let's give the input which is singleton fuzzified value at x0. So ms of A dash x0 is minimum over I of A dash x0 of x comma A of x. Note that A dash and A, they have changed positions. Implication is not commutative. So we take the given input at the first place and the antecedent at the second place. Now, this can once again be broken down into all those x which are not equal to x0 and x being equal to x0. Now, if you look a little deeper inside here, at A dash x0 of x, when x is not equal to x0, what we get is 0. So this essentially becomes minimum over x not equal to x0, I of 0 comma I of x, with minimum of, on the right hand side, what you see after the min operation is at A dash x0 of x0, we know it is 1, and so this is what we get, I of 1 comma I of x0. Now remember, in I is an implication, I of 0 comma y is always 1, no matter what implication you take. So all of these, for every x not equal to x0, no matter what a of x can be, each of these is actually 1. So minimum over all of these will be 1. Now what happens to this value here? If I has neutrality property, that means if 1 is the neutral element, left neutral element of the corresponding implication, then essentially what we get is a of x0, and we get the matched value, the similarity value between a singleton fuzzified input and any set A, which is a fuzzy set over X, is actually the membership value of x0 in that fuzzy set A. This is exactly what we have seen also in the case of Zadeh's matching function. Well, with this, let's move into looking at Mamdani fuzzy systems, how we can build one using the fuzzy logic toolbox in Matlab. Before that, a few terminologies. Look at the form of a similarity based reasoning fuzzy inference system. So we have seen this, px and py, they are the coverings, fuzzy coverings over the domain of x and y. This is the rule base where AIs and BJs are actually coming from the corresponding fuzzy coverings on x and y. H is the fuzzifier, M is the matching function, J is the modification function, G is the aggregation function, and small g is the defuzzy. Note that in Mamdani fuzzy system, as implemented in the fuzzy logic toolbox in Matlab, this is the family of matching function that we'll use. That means by specifying these two operations, we are specifying what the matching function will be. What is the fuzzifier that Matlab considers? Typically, it is a singleton fuzzifier that we'll consider there. And for the matching function, the operation, the internal operation, is called the AND method, and the external operation is called the OR method. And Matlab calls modification as implication, aggregation as aggregation, and defuzzification as defuzzification. So with this terminology, we are ready to move into looking at the Matlab code. It is typical when we want to learn a new algorithm to start with a very simple example. For instance, when we have learned how to find out the Fourier series expansion of a function, it is typical to start with the identity function. And so we will also do the same. So let's try to build a Mamdani fuzzy inference system which will approximate the identity function over the unit interval. So essentially, the function that we are going to consider is function from 0,1 to 0,1, and it is essentially f of x is equal to x. Now, how do we build the system? What are the things that we need to take into consideration? So in Matlab, if you have the fuzzy logic toolbox installed, all you need to say is type fuzzy, and you will see that it opens up the main window wherein what you need to be specifying are immediately accessible. For instance, you see here that AND and OR method together, they form the matching function, implication is the modification function, aggregation is the aggregation, and defuzzification is the corresponding defuzzification function. So now, when we have a clear idea of what we want to implement, what function we want to approximate, that is when we can start inputting the data. Now, what is it that we need to do? We have a function in mind which we need to approximate, and currently the function is the identity function. So we need to first come up with the coverings on the corresponding domains of x and y. Since it's an identity function over 0,1, the domain of x is 0,1, the domain of y is also 0,1. Now we need to build the corresponding fuzzy sets on this domain. So if you double click on this, you will see that it opens up another window which tells you a few things. So you see here input variable 1, output variable 1. Now, and it automatically comes up by default. It gives you 3 membership functions. All of them are triangular in nature. Of course, this is what we are going to modify. And you see here the range automatically is 0, 1, and in fact this is what we need for the moment. Now you could give any name, mf1, mf2. This is the default name that is given to us. Now we need to be able to specify the fuzzy covering on this, on the input domain, and a similar fuzzy covering on the output domain. Once these are done, then we need to fix up the rules. Now, how do we add the rules? So on this side, you see that we have all the input fuzzy sets, and this side we have the output fuzzy sets. We need to relate the input fuzzy set to the corresponding output fuzzy set to get a rule. You choose 2 of them and say add a rule, and you see that it has been added. You take mf2, and if you want to relate it to mf3, you say add a rule, and it will add a rule. mf3 and mf2 maybe add a rule. You can add a rule. You can also delete a rule or change a rule. Well, but the most important thing is, how do we come up with these membership functions? That is, how do we get the fuzzy covering for this identity on this domain of 0, 1 for x and 0, 1 for y, and so that we can relate these the fuzzy sets on x to fuzzy sets on y as rules which will actually capture the function that we are trying to approximate. Well, for that we need to understand how a fuzzy inference system approximates the system function. We know it is doing it by covering it with overlapping rule patches. Let's revisit the visual reasoning that we did, visual illustration of the similarity based reasoning that we have done earlier. Well, we know an FIS approximates a given system function f from x to y. How did we do this? We took the domain of x and that of y. If this is the given function, what we did was we came up with a fuzzy covering of x and a fuzzy covering of y, and we were relating the fuzzy sets on x to fuzzy sets on y through rules, and hence we are picking the antecedents from the covering on x and the consequence from the fuzzy covering on y. For instance, we have seen that if you relate cool to slow through a rule, that if x is cool then y is slow, essentially what we are saying is this, that we have the support of cool and we have the support of slow, and this is the rule patch that we get. Essentially we are saying 2 things here. If an input falls in the support of cool, then the output y is essentially restricted to the support of slow. So the ordered pairs which actually will belong to this particular rule are given by this shaded region. This is the first thing. So similarly, when we construct for each of these rules, we get these patches. And now the second thing is, we clearly see that with these patches, we are trying to approximate the function. We are covering the function. But also note one thing, that when we have this, at the end of it, when we give an input, we would get an output. It's a modified consequent of the slow, average, and fast. Finally, the aggregated output is a fuzzy set, and we need to defuzzify it. Now, depending on the defuzzification that is chosen, it could fall anywhere within this region. So, it is always better to finely granularize it so that we have smaller and smaller patches which cover this function. Of course, there is also a downside. If you want smaller patches, then what do we need to do? We need to have more fuzzy sets. That means the granularity on the input and output domains should go up. For instance, this is what we had in this case. Remember, once again, we are looking at fuzzy inference systems which cover the graph of F with rule patches. Now, instead of having just 5 fuzzy sets on X, let's assume that we have almost 9, and on the output side we have 7. Now let's look at how we are going to approximate this function through a fuzzy inference system. So essentially it means coming up with rules, but we understand rules are actually going to patch up this function, come up with overlapping patches of this function. What is our first point? So now let's look at the supports of the input fuzzy sets, or the fuzzy covering that we have on the input set X. This is the fuzzy covering that we have. These are the supports of the fuzzy covering that we have on X. Similarly, the supports of the fuzzy covering we have on Y. Now we'll use this grid to see how to relate a particular fuzzy set on X to a fuzzy set on Y. For instance, consider this fuzzy set and this fuzzy set. If you relate them, what you get is this patch. That means all the values, all the ordered pairs UV that excite this rule will fall within this patch. So if you have an input X which excites this fuzzy set here, which falls in the support of this fuzzy set, then the Y values will definitely belong only to the support of the fuzzy set you see here. However, notice that we are having a fuzzy covering. That means there are fuzzy sets on the input domain which are overlapping. So we need to consider them also in the overall, when finding the overall output. So consider the second fuzzy set here, and let's relate that to the second fuzzy set on the output side. What we get is another rule patch, and now it's overlapping clearly. Now if you go along this logic and start to relate input fuzzy sets to output fuzzy sets, perhaps this is one kind of a rule patch covering that we can obtain. A fifth rule, a sixth rule, a seventh rule, eighth rule, and a ninth rule. So you see here there are 9 fuzzy sets here, and each one of them has been related to some fuzzy set or the other. As you can see, on the output domain Y we have only 7 fuzzy sets, on the input we have 9. So typically, as was already mentioned, you will have, depending on the function that we have, you tend to always have more input fuzzy sets than output fuzzy sets. Now there are a few crucial things to note here. Firstly, look at this. We said that it is trying to approximate the function by overlapping rule patches. But now you see here, these parts of the function are actually not covered. So no matter what defuzzification mechanism you use, the output will lie within these overlapping boxes, patches, and so it is not going to approximate the function very well here. That's the first thing. The second thing that you would see is, when you apply any defuzzification or whatever choice of the defuzzification function that you take, even if this function were to remain within these rule patches, the output that you would get, the final function that you would get, may not exactly match this. Of course, that's because originally, to begin with, we did not know the function. If we knew the function, then we can tweak it. For instance, we only had an inkling that this is how the function should work, or the air conditioner should work. That's where we saw this monotonic function. So if you have the ideal situation in your mind, and if you're trying to approximate it, this is how you would approximate it. But depending on the defuzzification scheme and all other operations, the similarity based reasoning inference operation that you use, what you would get actually is that a function of this kind, perhaps, as you will see, it will remain within these overlapping rule patches, or you could also get a function of this type. Both of them are in some sense approximating the original ideal function that you have in your mind. So what we need to do is, in fact, take cue from this and come up with patches which are small in nature, which are likely to fall on the function, on the graph of the function, which means we need to accordingly granularize the domain of x and relate, and also the domain of y, and intelligently relate these two. That is what we would like to do. Note once again that a Mamdani fuzzy inference system is a similarity based reasoning system. You could use any of the fuzzifications for h, any matching function for m, and of course any modification, aggregation or defuzzification functions for the corresponding operation. However, what we have seen, or what we are seeing right now on the slide, is how Matlab Fuzzy Logic Toolbox implements it. And since we are going to make use of that to build a Mamdani fuzzy inference system, this terminology was used. Otherwise, Mamdani fuzzy inference system is a similarity based reasoning system, inference system, which does not put any restriction on the kind of fuzzification that you can have or the matching function you can have. So far in this lecture, the importance of how a fuzzy inference system approximates a fuzzy or system function is hard to exaggerate. It does it through overlapping rule patches. We saw what a Mamdani fuzzy inference system is, and we had a short introduction to building Mamdani fuzzy inference system using Matlab Fuzzy Logic Toolbox. The idea was to show the environment of Matlab Fuzzy Logic Toolbox. Looking at it, it was clear what are the components of the fuzzy inference system that we need to come up with, that we need to be ready with, so that we can build a fuzzy inference system, a Mamdani one at that. And we have seen it means to be able to have a clear idea of the function that we are trying to approximate and intelligently sample the fuzzy sets which will form the covering over x and y, and also to relate the fuzzy sets on x to fuzzy sets on y as rules, so that we can cover the function that we have in our mind through overlapping rule patches. And this is what we will be doing in the next lecture. We'll take a couple of functions and see how exactly to build this fuzzy inference system, the Mamdani fuzzy inference system, which would more or less approximate the function that we are considering. Glad you could join us today for this lecture. Hope to see you soon in the next lecture. Thank you again.